very much. All right, I'm very pleased to be here, and I thank the organizers for inviting me, and especially as, like Mr. Kumar, I don't have any medical background. My background is within smart and technical textiles, so that's what I'm going to focus here, as previous speakers have done as well. So I would like to thank the previous speakers as well, because they really focused on the really important issues, the importance of dosage, compliance, stiffness, and also maintenance of pressure level over time. So what about optimal compression? What is that? Well, we know that too low compression hardly have any effect at all. And we also know that too high compression can cause damage, tissue damage, or skin damage. So somewhere in between, we know that there is an optimal compression, an optimal dosage for each patient, but also there is an optimal amount of stiffness, of course. So somewhere on this curve, we have the optimal window. And what about compression treatment today? Well, we also heard that from previous speakers, that it's a big variance. It also depends very much on the applier and also the skill and the training of the applier. So this study here from Florence et al. From 2014 shows that less than 10% of the participating 551 healthcare personnel managed to reach the target pressure. And also, if you look at the minimum and maximum applied pressures, it's a huge difference between them, from very ineffective levels to quite dangerously high levels of compression. So you can sort of compare compression treatment today with a syringe looking like this and ask yourself, would this be accepted in any other medical area to have a syringe looking like this, or a medical treatment without any dosage? Wouldn't it be better if it could look like this instead? So what I will present is a product based on two components. The first one is a bandage, which gives a well-defined pressure, and the second one adds the stiffness to the bandage. So first you need to apply a precise pressure. And we also heard that from previous speakers that the importance of this and the difficulty of applying a correct amount of compression using an elastic bandage. However, this bandage here gives a well-defined pressure invariant of the applier and the leg shape. It's also elastic and conformable, meaning that we don't have any pressure change during movement, or if you have, for example, edema reduction, the material would simply adapt to the changes in curvature and keep the same pressure level. For this specific system, we have chosen pressure for the bandage of 20 millimeters of mercury, because it's safe and it's so comfortable in resting position. However, it is possible for us to design it in different levels depending on the need. So how does this work? Well, it's based on Laplace's law, and you know this guy from before, I suppose. So what is pressure? Well, the pressure is the product of the force, like how much you stretch the bandage, times the overlap, meaning how many layers you have. The more layers, the higher the pressure, times the curvature. And the curvature is different, you know, along the leg, and also different between different patients. So it's really difficult to control the amount of curvature. You can also describe it like this: if you use a constant force on a really high, on a sharp curvature, like the ankle, for example, the pressure will get really high. If you use the same force on a curvature that is less, you will have less pressure, for example, on the calf, or the same force on a smaller curvature, like the thigh, you will have even lower pressure. So this is how the bandage looks like. We have one longitudinal line for consistent overlap, so that we know that we have 50% overlap for each turn. But we also have the cross markings that determines the amount of material for each turn around the leg. And how does that work? Well, you're going to line up the short lines along the leg, as you can see in the picture, meaning that you need to stretch more on the thicker parts than on the thinner parts. However, if you remember from the slide before, if you have a thicker part, the curvature is also less there, meaning that in order to get a constant pressure, you need to stretch more over the thicker parts where the curvature is less. But it only works if you have a material with really smart and specific elastic properties. So that's why we have worked with this. We started thinking about how can we develop a smart and novel bandage without integrating any sensors or technology that would make it more advanced. So, but just making a truly smart textile by using the elastic properties of the material in combination with a construction of the textile. So this is a comparison between some elastic bandages on the market today and also with the material that I'm describing here, which is a long blue line here. So the first publication was from last year by Lundatex et al., where 21 nurses participated in the study, and they all had different working experience. So some of them do work with bandages every day, some of them work with brain surgery or other tasks. So it was the first time they used this bandage. They did one test application and then 3 consecutive measurements were done. And the predefined pressure of that bandage was 50 millimeters of mercury. And the results from the study show that for a 95 confidence interval, independent of state and position, we get about 5 millimeters of mercury from the target pressure. So compared to this study by Professor Prutz et al. Again, we had the results looking like this. So for all the participating nurses. And if you look at this dynamic measurement here, you can see that there is little change in pressure during movement, so the stiffness is very, very low. And as we heard before, from Mr. Newman, for example, that stiffness is really important, especially for the venous return and hemodynamic effect. So what we need is to apply some stiffness. This is usually done by adding a second stiff bandage on top. However, it's really difficult to control the force, the stretch, and the amount of pressure that you apply. So it's really easy to apply to high resting pressures. So if you look at this, it can be very large variance between different resting pressures, but also they can be really high, uncomfortable, and in some cases dangerous, especially if you have like mixed ulcers, arterial ulcers, or diabetes, for example. If you look at the stiffness, there's also quite large variance of stiffness. So there is really no consistency today. So therefore we have a novel material and method that doesn't change the resting pressure. And it looks like this. It's a simple patch in a Velcro material. And the patches, they are attached directly to the bandage material in supine position, meaning that we don't add any force, we only add stiffness. So the resting pressure stays unchanged, and as you remember, this specific bandage here gives a pressure of 20 millimeters of mercury. So it's still 20 in the resting position. However, you cover the leg in these patches, and the patches create a rigid and stiff shell around the bandage. So at working and standing position, the pressure is dramatically increased. And if you can see the last picture, there's a long patch in the front, and by opening and closing in the front patch, you can have some easy pressure maintenance over time, because you will always have pressure drop due to edema reduction and so on for stiff products. So if you look at the dynamic measurements now, with the bandage applied, you still have close to 20 millimeters of mercury in resting position. However, the stiffness now is improved to 29 instead of 1 millimeter of mercury, just by adding the patches. So this is a pilot study from earlier this year by Professor Mosti and Professor Patch, where all the patching you can see here, the resting pressure and the standing pressure for the bandage is close to 20, and also the resting pressure with the bandage and the patches is still close to 20. However, applying the patches, the stiffness and the pressure is dramatically increased. So this is just to show how you can maintain the pressure over time. So each morning you open the front patch, so there is no need for reapplication of the whole system. You open the patch, strike with your hand, and then close it again. And by doing this every morning before bed rise, you can keep and maintain the pressure level over time. So you can see here from this pilot study that in the evening, day 1, the pressure had really dropped because of edema reduction. However, by opening up the front patch each morning, we can really maintain the pressure. So at day 7, we have about the same pressure levels, both in supine and standing and working position. So the conclusion is that we can keep the resting pressure at a safe and comfortable level. It increases the working and standing pressure only by adding the stiffness, and it also allows easy self-maintenance of pressure level over time. So thank you very much for your attention here today, and I hope to see you on Tuesday for my next presentation and the workshop there.
So thank you all presenters, because they were really good.